Reviewing sections 7.1 and 7.2, hopefully you noticed that probability is really just a combination of two counting problems, at least as long as you have equally likely simple events. As long as you have equally likely simple events, you can simply count how many ways the event could occur and how many ways what you're looking at could occur and divide the two. And as you know, probability should always be between 0 and 1, so that can help you determine if you did a good job of calculating the probability. So what we'll do is go through 3 examples where the counting may or may not be done for us, or we may have to dig a little bit to figure out what the counting should be. So taking a look at this first example, we're told that a meeting has members from several different college clubs, 5 members from the math club, 10 from the science club, and 11 from the psychology club. We're going to randomly select a person at this meeting, and we want the probability that he or she is in the math club. So one way we could write this down is by writing probability math club like this. So this notation is essentially saying what we're finding the probability of. And once we find the probability, we'll drop that notation with the P on it. So again, it's how many ways can this event occur, and then how many things are in your sample space is another way to think about it. So the sample space, the big picture always goes on the bottom. And so the big picture is that we're picking somebody from this meeting, right? And how many people are at the meeting? We got 5 plus 10 plus 11. So we have 21, 26 people, right? So if I was to select one person, I have 26 choices for that one person. So that's the big picture, that's the sample space. And now the question is, how many choices do I have as far as the math club goes? This is the event. How many choices do I have? How many things are in the event? Many ways to think about it. And since there's only 5 members from the math club there, this would be 5. And so as a decimal, this probability would be 5 divided by 26, which is 0.1923. So in this example, a lot of the counting was in fact done for us. We just had to figure out what it represented. In other words, we had the 5, 10, and 11 already. We just had to put the information together. In other cases, we're going to have to use combinations or permutations. So for my next example, there's 2 parts, and we're told we're picking 3 people at random from a group of 12 Republicans and 10 Democrats, so a total of 22 people. And so A says find the probability that all 3 are Democrats. And then B says find the probability that 2 are Republicans and 1 is a Democrat. Now both of these events will have the same sample space. And so the size of the sample space, or the number of events in the sample space is another way to think about that, will tell me the denominator I need for the probability answers, for the answers for finding the probability here. So in the big picture, in both cases, I'm picking 3 people at random from a group of 22 people, right? So there's a total of 22 people. So the sample space is going to be 22 choose 3. That's how many ways there are to pick 3 people from 22. And so when I look at A, which says find the probability that all 3 are Democrats, I know that the denominator is going to be 22 choose 3. But now the numerator is going to be the small picture. What am I trying to study here? The event is that all 3 are Democrats. There's 10 Democrats in the group. So that would be all the ways I could choose 3 out of those 10. So that would be 10 choose 3. And so now really it's a matter of calculation. And remember, one quick check of this is to make sure that your answer is smaller than 1, right? When we count, we get values much larger than 1. But when we do probabilities, we get values smaller than 1. You could get a value equal to 1, but that would mean that the probability is 100%. And so that should make you pause and make sure that what you found makes sense. So when I calculate this probability, I end up with 0.0779. So this is saying there's about an 8% chance that if you were to select 3 people from this group, that all 3 would be Democrats. Okay, so B says what's probably that 2 are Republicans and 1 is a Democrat. So this could happen a few ways. The first 2 could be Republicans if you were to imagine we did it in order, but we didn't do it in order. But imagine you could think of the first 2 are Republicans, the next is Democrat, or the last 2 are Republicans. There's a lot of events represented by this statement. So again, because we're picking 3 people out of 22, I know that this is still the denominator. The question is, what's the numerator? Well, remember we have the multiplication rule for counting. This is just a counting problem now. It's like 2 separate counting problems. So how can I pick 2 Republicans and remember, and implies multiplication, 1 Democrat? Well, to pick the 2 Republicans, I would have to pick from the 12 Republicans, right? So since order doesn't matter, that would be 12 choose 2. But then by the multiplication rule, I got to multiply by the number of ways to pick 1 Democrat. And so you could say that's 10 choose 1, or you could simply say, well, I have to pick one of the 10, so there's 10 ways to do that. And when I calculate this probability, I get 0.4286, a much more likely event. And the reason I say that is a 4286. The reason I say more likely is because the probability is larger. So if the probability is larger, that means it's a more likely event. Here, I'll write this a little bit better, 0.4286. So this is actually, this right here is my final answer. So more likely means there's a higher chance of it happening, right? And so it's more likely that I'll have 2 Republicans and 1 Democrat, a mixed group. And that makes sense because most of the group, a little more than half, is Republicans. Whereas to pick all 3 Democrats would be much lower, since not a majority of the group is Democrats. But as you can see, what I'm doing is essentially a counting problem. So my goal every time I approach a probability question is to count the sample space and count the event. So in my third example, I'm told that a speech class has 8 freshmen and 5 sophomores. We're going to select 3 at random in a sequence, and a person can only give 1 speech, cannot be selected twice. And so these 3 people are going to be giving speeches. And again, in sequence is a really key phrase here, because it implies an order. So it says find the probability the first person selected is a sophomore, the second person is a freshman, and the third is a sophomore. So again, we're trying to find the probability. First is a sophomore, second freshman, and the third is a sophomore. All right, so the question is, how many ways can I approach this from the sample space perspective, and what about the small picture? So sample space is the big picture. Overall, how many ways can you pick 3 people from this group to give a speech in sequence? So remember, permutations don't allow for repeats anyway, so we know this is in sequence, we know order matters, and so we're going to use a permutation here. Permutation would say, okay, you're picking from a total of 8 plus 5, so 13 people in the class, and you want a sequence of 3 of them. So we have 13 and then 3. And then the question is, well, how can you pick a sophomore and then a freshman and then a sophomore? That would be the small picture. That's the number of outcomes in the event. Number of simple events in the event is another way to think of that. Well, think about the multiplication rule. We would first think, how many sophomores are there to fill that first slot? Well, there are 5. So there's 5 ways I could fill that first slot. And so now we think about the second slot. The second is a freshman. So the second is a freshman. Well, we haven't chosen a freshman yet, so there's 8 freshmen we could pick from. And so now we say, okay, what about the third? So the third is a sophomore. We already selected a sophomore to give a speech here, so we only have 4 sophomores left to give a speech. And so again, I couldn't really use permutations here because we're selecting from 2 groups, but you could have done a permutation of 5, 1, 8, 1, but that's very much overkill. In the end, the multiplication rule made the most sense here. So when I calculate this probability, and you should always be double checking that you get the same values as me, I get 0.0932. So about a 9% chance of that happening. As you can see, it's all about counting, and it's all about reading carefully to see permutations or combinations. But a problem, just like anything we've done before, could be mixed, right? You could have problems that part of it needs a combination, part of it needs a permutation. Anytime you're not sure, remember to double check, make sure your value is smaller than 1, and make sure that you've counted very carefully and you've thought about the big picture versus the small picture.